Hello everyone. So today we will solve this problem. Here uh, a refrigerator is using refrigerant 134A. So this is a refrigerant 134A and it's working on an ideal vapor compression refrigeration cycle. Was between 0.14 and 0.8 megapascal. Mass flow rate is 0.05 kg per second. To be determined, the rate of heat removal, the rate of heat rejection, the scope of the refrigerator. So to solve this problem, we first have to know how the TS and pH diagram of a ideal vapor compression refrigeration cycle looks like. So here it is. This is the TS diagram and this one is pH diagram. So in this case, point 1 is situated just on the saturated vapor line. Point 2 is situated in the superheated region. Point 3 is situated on the saturated liquid line, and point 4 is situated somewhere between this curve. So we can start now. Here mass flow rate is given 0.05 kg per second. P1, P4 is given 140 kilopascal, P2, P3 800 kilopascal. So what is H1? So we first look at point 1. See, point 1 is situated just on the saturated vapor line. So here there is only vapor enthalpy and there is no liquid enthalpy. So we can say that the vapor enthalpy of point 1, that means Hg1, is total enthalpy of point 1. So vapor enthalpy of point 1 is equals to the total enthalpy of point 1, H1. So we need to find actually vapor enthalpy of point 1. So where we can find it from? We can find it from the property table. Look, so this is superheated, so this is saturated refrigerant. So here it is saturated refrigerant 134A pressure table. So we have to find the pressure. Our pressure is here 140 kilopascal. So this is the line. So from here we have to find the vapor enthalpy, and where it is. Alright, this is the vapor enthalpy of point 1. That means the total enthalpy of point 1, H1. So H1 will be 239.16. Alright, 239.16, and it is H1. S1, look at the TS diagram. We can see that S1 and S2 is equals, because we know here the compression is isentropic, so we need to find S1, that means total entropy of point 1. So as point 1 is situated on the saturated vapor line, so there is no liquid entropy, there is only vapor entropy. So we just need to vapor entropy of point 1. In the same process we can find it the way we found H1. In the same process we can find S1, and that's it, and S1 equals to S2. And now HF3. So how can we find HF3? Actually we need to find H3. So look at point 3. What is point 3? Point 3 is here. As you can see, point 3 is situated on just the saturated liquid line, so there will be no vapor enthalpy, there will be only liquid entropy, and liquid entropy of point 3 is equals to the total entropy of point 3. So we can say HF3 equals to H3. In a similar way you can find it from the property table. I'm not showing this, hope you will be able to find this. Now we have to find H2. So how can we find H2? So look at this. At point 2, we know at point 2 pressure is 800 kilopascal, and entropy of point 2 is 0.9.456. So just look at point 2 where it is. So we can see here point 2 is situated in the superheated region. So here the refrigerant is under superheated condition. So we have to go to the property table and find the enthalpy of point 2, and which will be corresponding to pressure 800 kilopascal and entropy 0.94456. So we are going to the property table and we'll find, of course, the saturated. Here that was saturated refrigerant, and now we need superheated refrigerant 134A, and here it is, superheated refrigerant 134A. So we have to find pressure, and that is pressure of point 2. Pressure of point 2 is, we know, 0.8 megapascal. 0.8, where is 0.8? all right, we have found 0.8. here it is. So we have to find the entropy. So our entropy was entropy at point 2 was 0.9480. So the enthalpy corresponding to this pressure and to this entropy is 276.45. So I repeat, the sorry, I repeat, the enthalpy corresponding to this pressure and this entropy is 276.45. Alright, so that is 276.45. We got it. Now we have found H1, H2, H3, H4, so we can now easily find out the rate of heat removal. Look, the rate of heat removal we know that is mass flow rate multiplied by H1 minus H4. So how it is H1 minus H4? We know the heat removal occurs in the evaporation process, and we know evaporation is from 0.4 to 0.1. So okay, look at pH diagram. So evaporation is occurring in between this point 0.4 and 0.1. So our heat removal is this distance will represent heat removal. So what is this distance? This distance we can easily find by subtracting H4 from H1. So H1 minus H4 is equals to this distance, right? H1 minus H4. So H1 minus H4 will be the heat removal, H1 minus H4. So you can see here H1 minus H4 multiplied by mass flow rate m dot. So we found 7.18. Now the power input W. So we know power input occurs in the compression process. Compression process occurs from 0.1 to 0.2. So we can say that here the power input will be represented by this distance, right? So this distance will represent the power input. So what is this distance? This distance is H2 minus H1, right? H2 minus H1. So of course H2 minus H1, right? H2 minus H1 multiplied by mass flow rate. So we found this 1.86 kilowatt. So now rate of heat rejection. So where heat rejection take place? Heat rejection take place in condenser. So here it is 0.2. Heat rejection occurs between 0.2 and 0.3. So heat rejection, so which distance will represent heat rejection? This distance will represent heat rejection. So how can we find this distance? We can find okay, H2 minus H3, right? No, sorry, H2 minus H3, that will be this distance, and this distance will represent the heat rejection, right? All right, so that is what? That is H2 minus H3, that will represent heat rejection. See, H2 minus H3 multiplied by mass flow rate. So we found 9.05 kilowatt. Now the coefficient of performance we know, that is heat removal QL divided by work input. We have already calculated this, so just putting the values we found and coefficient of performance very easily. So that's it. Thanks for watching. So if you like this, please stay with me and subscribe my channel.